Okay, now let's talk about hyperparameter optimization. So let's say we're done, we've done lots of these cycles, we've done the failure analysis, engineered some new features, found some improvements. Kind of feel like, hey, we're at the point we're not really going to make any more significant improvements with the variables that we have. You know, I'm ready to go forward with this model and put it in production, but I want to make sure I'm not leaving any performance on the table by not having the best possible hyperparameters. So we're going to do some hyperparameter optimization. Now, some practical considerations to ask, some questions to ask when you're doing hyperparameter optimization is, first of all, how much is it really worth to improve this metric by a certain value? So in this case, I've got, a mean squared error of, let's say, 19,900. If I improve it to 18,000 something, how much money is that worth to the business? How much is it, how much time is it worth spending? How much? And these are very hard calculations to make, but it's worth trying to at least do a little pen to paper if you've got something to hold on to, some way of doing that calculation. It's really a worthwhile exercise to think about how much this is helping you, because sometimes it's like, if I'm only going to move it down a little bit and I'm spending a week doing hyperparameter tuning, maybe it is worth it. There are certainly use cases where it is worth it. There are also many use cases where it's not really worth it. So related questions: how much time computing do I really want to spend on this sort of improvement? How often will I be retraining, re-implementing this model, right? So if this model is only going to have a relatively short lifetime, the less time you want to spend, really perfecting it, right? And we've talked already about the value in knowing and understanding this data set model really well. Okay, so setting the parameters and gradient boosting. There's a few approaches. One, the most common that people probably know about is just doing a massive grid search, right? And then on the other extreme is like, hey, you just play around until you get tired, and then you stop and you say, this is the best one I found. And there's a third alternative, which we're going to spend a lot of time on here, which is doing smart parameter searches that search promising combinations. So rather than just blindly following the grid, we're going to sort of jump around and use what we've seen so far to guide what's the next thing we do. And there are some nice packages that kind of do this for you and make smart choices. Now, there are drawbacks to all these. Grid search is extremely time consuming, and it's difficult to know often whether you're choosing the appropriate parameters and ranges. And again, as I've discussed before times, there's other considerations other than just metric performance. The model size, what I call coherence. That's something about like, does the model's interpretations make sense? We'll talk about that in a future lecture. And the training time. So now, on the other hand, the manual approaches are very haphazard. They consume your attention. It's useful to the extent that it helps you build confidence in your data and in the model. But after a certain point, just doing manual approaches is not gonna give you the same kind of gains that something more automated could be. And we're going to talk about these smart approaches. That they're not always as smart as they could be, but I would say in general they're pretty good, and they're better than the other two alternatives. But what I'm going to recommend is sort of a combination of these approaches, and we're going to see how that plays out. So first of all, as I said, the max depth is the most important. Now, we tune the max depth at the beginning, but now we've added in some features, we engineer a new feature. So a good thing to do is always, when you get a chance, like, let's revisit the max depth and just see how much we can get from just retraining that. So we're going to run the same thing. This is with our new engineered variable that combined the basement square footage. So we're going to let that run. Okay, so that finished. So let's do a plot now. So we see that we're getting the best value at max depth 4. So previously it was 3, it was at 3, but 3 and 4 were really close. And now that we've added in this new variable, now 4 is doing a bit better than 3. 3 is still kind of the second place value. But we're down over here, so now we've already got to 19,500. So we've already got a, again, a substantial improvement by just retuning the max depth. One thing I want to point out, I meant to point this out previously, is notice the range on the y-axis of differentials in max depth, right? So choosing 4 instead of 3, which was the second best value, paid off, by about 300 points of mean squared error, right? Pretty significant. And if you had, one of these worse values, like a 2 or 8, right, it was like another 300 to 500 points worse. So just keep that in mind as we start exploring some of the other parameters, where you'll see that in the other parameters, there's typically less of a difference in getting the exact right value. Max depth, that's also integral, right? So one thing to think about is how good is the best value versus the second best value. And here we see the best value is significantly better than the second best value. Let's now, what we did for max depth, let's now explore some other variables just to get a sense, build up our intuition of how important some of these variables are. So first we're going to do the subsample variable. So this is the percentage of data that we use for each tree. Let's see as we change this variable from 0.7 to 1, let's see how much of a difference this makes. So we're going to let it go and plot. So if we look at this plot, we see we get the best value now at 0.75, which is a significant improvement over what we were at before, which is 1. But you can see that for most of the values, anything between 0.7 and 0.95 gave us a pretty good value. The jumps here are relatively smaller. They're on the order of 100 rather than on the order of like 300 or 500. And another thing to keep in mind through all of this is you shouldn't take these as, some of this is just going to be noise. Some of this variation is just going to be noise. So don't be too convinced that, a number is perfect because it got the best value. A lot of this is due to noise. We don't have a huge test set here. Similarly, let's now look at, our best value is 0.75. You can see we've already gotten down to, below 19,000. Let's now set subsample to be 0.75, and let's play around with this call sample by node. So this is what percentage of features we're going to sample at each node. We're going to let that go from 0.2 to 1. So let's let that run. And we'll have it plot once it's done. Okay. So, and here we see an interesting pattern, right? And this shows you kind of how noisy some of this stuff can be. We actually get good values at 0.9 and at 0.3 and worse in between. But again, if you look at the scale of this y-axis, the entire scale from the worst to the best value, is around the order of like 300 points, right? So this could be noise, this could be something else, but there's going to be a lot of good values here. 0.3, the difference between 0.3 and 0.4 is not that much of a difference. 0.9 is also good. So again, this is not having the same kind of impact that the max depth was having. So now we're down to 18,909. Now let's look at, we're going to look at the reg lambda. So this is one of the XGBoost shrinkage values that sort of shrinks coefficients in the same way you might think of your lambda in ridge regression or lasso regression. We're going to use the XGBoost equivalent of that. And in this one, we want to try sort of different orders of magnitude. So I'm going to try this range of values. And let's let that run. And again, I'm using the best values I saw before, so 0.75 and 0.9 here. Okay, so and now if we look here, we see we do the best, for these sort of small values. And here, actually, this one does make a significant difference. As if we make this penalty, if we put too much shrinkage, it starts really hurting our performance. But as long as we keep sort of these small values, it's not that huge of a difference. So 18905 versus 18909. So optimizing this versus leaving the default didn't really bias much at all. Okay, so this is to give a flavor of, one, to give you a sense of how much difference these parameters make. And you want to think of it both in terms of what's the best value versus a really bad value for different parameters, and what's the best value versus like a pretty good but not best value. And the reason I focus a lot on the max depth is because often the best value is better than any others, and certainly the worst values are really bad. And for a lot of these other parameters, it's kind of, there's a range, and anything in this range is going to be generally pretty good, and the impact is not going to be as much. So I wanted to do these experiments to build a little bit of that intuition. Second, I wanted to show that, that this gets tedious. You don't want to keep doing this over and over again, right? But at the same time, it's hard to even know, without doing a little bit of this, it might be hard to know what are even the appropriate ranges you should search in, right? So like this reg lambda, like how do you know if 20 is too big or not, So here, now we know, okay, if I'm going to sort of try to search this variable more intensely, I want to keep it, in the range of 0.01 is too small, but I kind of want to keep it between 0.1 and 2, something like that. Like I should focus my search in that area. So this is where we're going to use the hyperopt package. So again, grid searches just get crazy, crazy big and take crazy long, and you don't want to have to exhaustively search every possibility. So the idea behind hyperopt is, after you've maybe done a little bit of this experimentation, you have sort of ranges that you think, I'm pretty sure this is the best number somewhere in this range. I want to search that area, but rather than just doing a full grid search, I want to add a little bit of randomness. So I'm just kind of jumping around and searching some areas, but then kind of smart randomness, where if I see an area that looks promising, I want to spend a little bit more time in that area. And if I know that an area is not so promising, I don't want to spend as much time in that area. And there are a bunch of problems you may have heard of that are called exploration-exploitation problems, where the challenge is, how do you balance sort of looking in the areas where things are best and exploiting that, versus trying to find something new which might be even better. So hyperopt kind of tries to balance out that sort of exploration and exploitation. And we're going to see it in action. So the first thing hyperopt needs is a loss function. So you have to give it a function that takes a set of parameters, typically as a dictionary, and gives you the value, what you think the metric is, the losses for that set of parameters. So it needs to be framed in terms of a loss function. So if you have something that bigger is better, you just take the negative of it. So you want to hand it a function like this. So we're going to build this function. It's called eval model. And all it does is it defines the base XGBoost model. It sets the parameters that you give it in the dictionary. Then it also sets the learning rate to 0.01. Here I put the n estimators as 10,000 and the early stopping rounds as 20, so it goes a little bit further before deciding to call it quits. But otherwise, it then fits the model to our expanded feature set. That it also includes that square footage variable that we engineered, makes the predictions, and gives us the mean squared error. So this is our loss function. So it's going to evaluate this function over and over again at different settings of parameters, and it's going to try to use some smart logic and also some randomness to try different parameter values and sort of find good combinations. So we define this function. And once we define the function, then we also have to tell it what's the range of parameter values we want to search. And you have to define this. There are a lot of different options, and you can see more of the documentation here. But basically, you just need to be careful about saying, do I want to choose an integer, or is it like a floating point number? If it's uniform, do I really want it to choose like arbitrary floats? Like, do you want it to choose a subsample value of 0.724133527, or do you just want to say, hey, check 0.7, 0.75, 0.8, 0.85, 0.9. You could also give a specific set of values if you don't want to give it as a range. This choice is typically used if the parameter is not numeric. You could also decide to do things on the log scale. So I didn't write that out here, but we're going to see it down here. So for this reg lambda, I'm going to have it work at the log scale between 0.1 and 20, because that's what makes sense for the lambda. The lambda really operates kind of as a log scale. So I'm going to go ahead and define this. So for the max depth, I'm going to have it search between 2 and 5. Again, this is Pythonic, so 2, 6 means 2, 3, 4, or 5, but not 6. For call sample by node, I'm going to use the Q uniform. So that means to go from 0.1 to 1 by increments of 0.1. For subsample, I'm going to go from 0.3 to 1, so by increments of 0.05. And for lambda, I'm going to use this Q uniform between 0.1 and 20, increments of 0.1. So we define the space, so we define the sort of range of values and how it should sample those values. We define the function it's going to evaluate. And then you define this trials object and you run your fmin object. So if you pass this, fmin is the execution of this. And so what you need to give it is, here's the function I want you to evaluate. Here's the space. You give it the algorithm, how should it suggest the next one? So they have a few different variants of algorithms. We're going to use the one that's called tp.suggest. But this is sort of the guts of how it decides what's the next parameter to try based on what it's seen so far. And then we're going to tell it how many evaluations to do, and we're going to pass it this trials object, and this is where it's going to save all the information about it. What's nice about this is you can specify how many iterations to do. So you could just say, hey, try 100 different possibilities, and then you could stop and analyze and look, and you can adjust things. And then if you want, you could do another one and maybe do a bigger one. So now this does take a little bit of time to run. So I'm going to start it running, and then I'm going to pause the video and let it skip to the end. But let's kick this off. So you can see it's running, and it's going slowly, and part of this is because I've got other software running to record this video, which slows down the rest of my computer. But you can see it's taking 6 or so seconds per trial. Now, if I wasn't recording, this is typically more like 1 or 2 seconds per trial on a data set of this size. But you can see, this is also a relatively small data set. So just to try to give you a sense of, how much time this takes to run. But I'm going to pause the video and let this finish going, and then we'll continue. Okay, so it took, it took about 8 minutes for that to run. By the end, we're down to about 5 seconds per trial. I will say, typically on this example, it's a bit quicker. It's typically about close to 1 second a trial. But you can see that one thing that's nice about this is as it's running, you can see the best loss it's found so far. And now you can see that it's finished. It found a loss of 18,628. So again, we did a little bit better than what we had before, was 18,905 from kind of our poking around. So again, a good thing. We got a little bit more improvement, but again, it wasn't super dramatic. It wasn't on the same scale as what we got from adding in some of these variables. So you can look at the best. So we assigned the result of this fmin function call, to a variable called best, and this best will now tell us what those best variables were. So it found the best call sample by node was 0.4, the best max depth was actually now 5, reg lambda at 0.3, and subsample at 0.6. We call eval model on our best. Again, this will take a few seconds to run, but it gives us our 18,628 value. Now, I want to spend a little time and go into the guts of this so that you can understand how it works. So there's this trials object that we passed into the fmin function over here. And I'm going to look at just the first 3 items in this list. So the result of the list. And you can see this gives us like every single evaluation that the algorithm did. So you can see this is the first iteration, and it tried call sample by node of 0.2, a max depth of 2, reg lambda of 2.5, and subsample of 0.7, and it got a loss of 20,051. And then you can see the next one got a loss of 19,356 with call sample by node of 0.7, max depth of 3, reg lambda of 0.2, subsample 0.75, and so forth. So with this, you can learn a lot about the process that Hyperopt went through to find during those 100 hot trials to try different values. And we can just explore this a little bit. So if you look here, here's the loss versus the trial number. And you can see it's kind of, on average, kind of trending down. As it goes on more, it starts spending more time in the areas that it knows are better. Another thing I want to point out is a lot of the trials gave us numbers, under 19,000. So again, an argument for, it's not about getting the absolute single best setting of hyperparameters, which is way better than everything else, right? You can typically, there are lots of combinations that will result in good loss values. Now, let's look at, this is the call sample by node that it tried versus the trial number. So you can see at first it's kind of jumping all around, and then later on it's focusing its attention a little bit more over here where it ended up. It stops trying the really big values and the really small values. At the end, it's kind of focusing more on the middle because that's where it found the best values. Max depth, here are the max depth values it tried. So we searched 2 through 5, and actually you see that it starts learning pretty quickly that 5 seems to be the best. And so it occasionally jumps around and tries 2, 3, and 4, but it's spending most of its time trying out number 5. And the fact that we found the best here at 5 suggests that maybe we should do another run and widen that range. If 5 is actually better, maybe we should be looking at 6 too, just to see if that's, better. Now let's look at the max depth trials versus the achieved loss. So when it tried different max depth values, what losses did it find? And you could see that, all of the best ones were at max depth 5. So this is again another argument. We should probably run another one where we go out to 6 and maybe even 7 to see if this continues improving. But you can see that the max depth it's pretty significant, right? When you had 2, you never got better than 19,750, but when you've got 5, you were almost always better than 19,750, right? So this max depth is an important one. Call sample by node. See here, you see there's more variation, right? It didn't matter as much. Yeah, you got the best one here at 0.4, but there were some pretty good ones here at 0.32, and even these other values over here tended to give reasonably good values. Let's look at subsample. So subsample, again, you see that there's a wide range of things that do pretty well. It's not as dramatic. You contrast this graph with the max depth graph, right? You don't see the same super strong pattern or signal. And finally, let's look at lambda. So again, lambda, now this is on the log scale. So 0 means 1, -1, -2 mean values less than 1, yeah. And these represent the bigger values. So you can see it's focusing its attention on things 1 or less than 1, and not so much on these bigger regularization values. So you could run something like this, right? And then the nice thing about this is you can run a short little exploration, and then you can refine your ranges and do it again. And you can keep track of, the best thing you found overall. So let's do another one. And this one, based on the max depth, I'm going to let it go 4 through, this should be 8. So 4,9, we're going to check 4 through 8 because I saw over here that we were still getting better with 5, and I just want to make sure that this doesn't keep going down and that it does sort of come back up again. And, refine some of these ranges. So actually, I'm going to keep the other ranges the same and just change the max depth. And we can let that run. So let's let that run. And again, I'm going to let it run for 200 evaluations. And again, I'm going to pause and let this run by itself. Okay, so that finished running. And you could see now we get a loss of 18,606 compared to before. We had 18,628. So we got like a very, very marginal improvement. And here, interestingly, I found the best thing in the max depth of 7. And, these values. Again, let's just kind of look through and see what we get. So this is the loss function overall as a function of the number of trials. And you can see it looks like it found this one, which seemed to be kind of a bit of an outlier at the time. And as time went on, it started getting other ones that were pretty good too. These are the call sample by node values it tried. So this is what it's tried. I want to get into the losses. So see here. So it's interesting. So you see it found the best one was at 7, but overall 5 and 6 were doing better. So that's interesting. So this suggests that, maybe we shouldn't put too much of faith that this is indeed the best value. That maybe these things over here around 0.6, around max depth 6, might be a little more reliable. So again, this might guide us as to what to do with a future search of this type. And again, we've done 100 and 200. You could do longer ones, right? Much longer ones, and see how those pan out. But overall, you see we're running into sort of smaller and smaller returns. So here, call sample by node, so again around 0.3 is doing best. Subsample, again, this was sort of an outlier. Most of the good values seem to be around here, so that's sort of interesting. And for the lambda, again, we're kind of seeing this is on the log scale, so around 1 or a little bit less than 1 seems to be the best. But let's say, we decide to go ahead and just use this. So I can make a final XGB model where I use the parameters I did before and retrain it. And then I can go forward and say, this is my model, and put this into production or do whatever you would do once you finalize the model. So let's just add some final comments on this. So this was a small data set, 3,000 data points, right? So we were able to run a lot of iterations. So typically these searches will take longer. So that makes choosing your ranges of values really important to choose smart ranges and not spend too much time on values that are wrong. The smart search will help with that to some degree, but it also helps to make sure you include the right values. Again, lots of combinations gave good results. And typically if you get the max depth right and you get pretty good values for the rest, you'll be in good shape. You don't have to worry. It's generally not the case that there's one magic set of values that works way, way better than anything else. And in practice, other considerations such as model size and parsimony may come into play. You may want to pick a simpler model if the difference in performance is negligible. So in general, like if I'm between two max depth values, I'll typically err on the smaller of them because it's a little bit more, I'd rather err on the side of underfitting slightly than overfitting slightly, because if you're underfit, at least you'll generally tend to be a little bit more robust if things change a little bit. So if you have model drift, or if there's some difference between your training conditions and your production conditions, you'll tend to get a little bit more flexibility from the simpler models. So that's it for this course on building gradient boosting models. I hope this was useful. And the next course will be about understanding models. So I'll start at this point and say, given that I have a model, how do I understand what it's doing, why it made the certain predictions it did, and so forth? How can I really explain it? And we're going to see that there's a lot you can do, even with these complicated gradient boosting models that are not linear, but have a high degree of interactivity. You can learn a lot about these models, and that those things that you learn can be very insightful. So I hope you'll join me for the next course. And for now, thank you very much.